Hey, grade 9, we're going to talk a little bit today about distribution of matter in space. We're going to talk about how stars kind of go through their life cycle, all sorts of good stuff. So let's get into it. First of all, this is really important, this kind of like idea of what's biggest and then next and next and next. So you've heard the term, I'm sure, universe and galaxy. Universe includes everything, planets, stars, galaxies, intergalactic space. It is everything. Well, a galaxy is a large group of millions or billions of stars held together by gravity. Normally in the middle of a galaxy, you have actually a black hole that everything is moving around. But it's a collection of many stars and solar systems and so on, all together in the same galaxy. And we live in the Milky Way galaxy. That's where we are. Oh, the text is missing. But the Milky Way galaxy, and you can actually see right here kind of a representation of how the Milky Way looks. And this is right around where we are, is approximately here. That would be our position. All right, so let's talk about kind of where everything fits in. So biggest is obviously the universe, because that includes everything. Then from there we have galaxies, which are, again, millions and billions of stars and solar systems all kind of clumped together. And then we have solar systems being smaller than galaxies. So a solar system would include a star, and then whatever planets are revolving around that star or orbiting that star. And then we have the stars themselves. Finally, we have planets getting even smaller, and then we have things like moons and comets and asteroids and meteors below that. I probably should put moons or natural satellites somewhere in here. Black is not going to show up very well on black. So let's go ahead and put moons right here as well. Just kind of the idea of, again, what is largest to smallest. So a very typical question on an exam would be basically putting some of these things in order from biggest to smallest. So make sure you know your terminology. So the Milky Way is the galaxy that we are in, which is a spiral galaxy. Talking about our solar system, it is a star with a group of celestial bodies, that are held by its gravity and revolve around it. So we have basically just a star and then a bunch of planets, celestial bodies that are moving around that star. So for example, we have the sun, which is our star in our solar system. And then of course the planets in our solar system are orbiting around the sun. So what is a star? Let's talk a little bit more about stars. A star is a hot glowing ball of gas. Mainly it will contain hydrogen and helium. But we can include other things as well, which you're going to learn about later. And it gives off tremendous light energy. And this is due to the reaction, the nuclear reaction that's happening within the star, which is nuclear fusion. Fusion is coming together, fusing together. So when we have nuclear fusion, it is atoms that are fusing together to make larger atoms. So for example, in our sun, we have hydrogen atoms that are fusing together to make helium. And when that happens, it releases massive amounts of energy in heat and light and so on. Sometimes there's a large amount of particles, charged particles, that get released from the star or our sun as it goes through its nuclear reaction. And when that large amount of particle gets released, that's called a solar flare. But any particles being released is called solar wind. So it has to do with charged particles that are being released from the star. So when there is a huge solar wind given off by the fusion reactions, it is called a solar flare. I'm going to guess that this is a nice picture. Oh, sorry guys. Ooh, let's go here. Oh, no, this is the aurora borealis that is made. And then here we have the aurora australis. We'll talk more about that in a second, but solar flares, when they're released large amounts of charged particles, and when it hits Earth's magnetic field, it is deflected, but gives off light known as the auroras, right? The aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. And this has to do with the charged particles kind of bending their path and releasing energy in the process. And it's very neat to see if you have seen it. I think I have some kind of an image. Oh, maybe it didn't save. Oh well. Anyways, let's talk more about stars. Stars can vary in size and color. Two scientists, Hertzsprung and Russell, compared star color and light intensity and found that the brightness and temperature are related to kind of the color and the brightness of the star. So when you take a look at a star, you can actually tell a little bit from its colors how hot it is and the temperature and so on. So this is a nice little diagram which shows you that as we get to a decreasing temperature, it's getting more and more red. Okay, when we have kind of in the middle, our sun is quite yellow. It's right around here. And then as we end up getting to a higher temperature, right, we have even brighter and so on. And this is more blue and then purple. So it has to do both with the brightness that we have as well as the colors we see as well are related to the temperature. So let's talk a little bit about the life cycle of a star, the birth, life, and death of stars. Stars form in nebula, which is a huge cloud of gas and dust. And eventually what happens is that cloud and dust starts collecting, and because of gravity, it comes together and forms something of very, very high mass. And eventually at the start, we start having that nuclear fusion kind of happening or beginning, and we have a protostar at that point. And that's when the star is just beginning to glow. And as the protostar gets hot enough, like around 10 million degrees Celsius, pretty hot, the star contents start to change hydrogen to helium in that fusion process. And that fusion process gives off a ton of energy and radiation as it's occurring. The protostar then turns into a sun-like star or a massive star once it gets to that temperature, once we start having that fusion occurring. So this is kind of where it splits off into two different parts. We have what we would call a sun-like star, which is like our sun. And then we have a massive star, which is much, much bigger than our sun. So when we have a massive star, it actually kind of changes what it goes through. So when it starts dying, when the nuclear fusion reaction starts slowing down, it forms what's called a red supergiant. So the super is in there as opposed to our sun, which turns into a red giant as that fusion reaction starts slowing down. And we have some notes on this in a minute here, but essentially you can think that as the fusion reaction starts slowing down, it starts expanding and expanding and expanding out. And then as the fusion reaction actually stops, it suddenly collapses together. And then from there, it's either going to make a white dwarf or a black dwarf, if it's a sun-like star, or a smaller star. If it's a larger star, as it collapses together, there can be a massive explosion called a supernova, okay, as it collapses and there's super high pressure and then fusion occurs and kind of blows up. And then from there, we can either get, as a result, a neutron star or a black hole. So neutron star would be for smaller massive stars, and then a black hole would be for a very large massive star. So anyways, once the hydrogen core gets used up, nuclear reactions cause expansion of the outer layers, turning the sun-like star into a red giant or a massive star into a red supergiant. So as we were just talking about here, as the star starts to die, it starts turning into either this or this, which means the fusion reaction is slowing down. Then after that, finally the fusion reactions stop. For sun-like stars, the star does not collapse, but forms a white dwarf. When it fades completely and becomes cold, it is called a black dwarf. Or when we have the massive stars, gravity collapses the star's core too quickly. This causes it to explode, an event known as a supernova. The star is not destroyed. The core is left as a neutron star, the small spinning object. If the star is destroyed, it forms a black hole. So we either get a neutron star or a black hole out of it. All right, so really important that you understand this diagram. You don't have to know all of the workings of it, but just kind of the idea of nebula, your little star nursery there. As things collect and the fusion reaction starts, then we end up getting a protostar, and then it turns into our different stars. We can have smaller ones or larger ones. Larger ones differ in that it's red supergiant to supernova, and then either to neutron or black hole. Well, sun-like stars turn to red giant, and then a white dwarf, and then eventually as that dies, it turns into a black dwarf. All right, planets. How many planets are there in our solar system? Well, there's 8 currently, but as you heard on that podcast, we are maybe going to find more as they kind of do different things and look at gravity and how things move in the outer reaches of our solar system. Planets are formed from the dust and gas that is left after a star is formed. The planets come in different sizes, composition or makeup, density, and temperature, as you know. So the inner planets in our solar system, including Mercury, Venus, Earth, and Mars, are also known as the terrestrial planets because they are rocky. It lies within the asteroid belt. So they are the inner planets because they're within the belt, the asteroid belt. And then we have the outer planets, which includes Jupiter, Saturn, Uranus, and Neptune. And they are mostly composed of gases and are also known as the Jovian planets. It is outside of the asteroid belt. So when we talk about inner or outer, we are literally just talking about where it is in relation to the asteroid belt in our solar system. So let's talk a little bit about different distances that we use to talk about stuff in space. First of all, the astronomical unit, or AU, is the distance between Earth and the Sun. So we talk about things in our solar system, it's really useful to talk about the AUs that we have. And that equals about 150 million kilometers. There's some variation as Earth orbits and gets closer to the Sun than further away, but it equals 150 million kilometers or thereabouts. It is used to measure distances inside the solar system, and outside the solar system, distances are just way too big to use AUs. So instead, we use light years. And what a light year is it's how far light would travel within a year. So light has a speed. Light travels at 30,000 kilometers per second? No, 300,000 kilometers per second. So light travels at 300,000 kilometers per second. So you can think about it as if you traveled at 300,000 kilometers each second for a year, that's a light year. So that equals about 2.6 trillion kilometers. 2.6 trillion kilometers. And by the way, you don't have to memorize 150 million or 2.6 trillion kilometers. Just know that a light year is how far light would travel in 1 year. And that's really useful for things outside of our solar system. So this is showing some different AU units, taking a look at stuff. So for example, Earth is at 1. Jupiter is just over 5 astronomical units away. Saturn would be just under 10, around 9 astronomical units. Uranus is around 18, Neptune 30, Pluto even further out, around 38. Okay, not considered a planet anymore, because if it was, as you learned in that podcast, we'd have to include many different things as planets. So we had to raise the bar. You have to be this big to be a planet. And Pluto did not make the cut. But that kind of gives you an idea of how far away these things are in comparison to Earth from the Sun. So going back to light years, light travels at about 300,000 kilometers per second and makes it from the Sun to the Earth in about 8.5 minutes. Normally it's 8 minutes and 34 seconds. So that gives you an idea of how astronomical units relate to light years and how massive light years are in comparison. So think about 8.5 minutes in context to a full year and how small that is, and that gives you an idea of how massive a light year is. All right. Let's talk a little bit about natural satellites known as moons, and specifically our moon. So we're just going through different objects in our solar system. The moon is Earth's only natural satellite. A satellite is any object that rotates around a celestial body, like a planet. A lunar eclipse occurs when the Earth blocks sunlight from reflecting off of the moon. So a lunar eclipse means that the moon, lunar, is getting eclipsed. So Earth goes between the Earth and the moon, and as a result, the moon is blocked out. It's completely eclipsed, and it's dark. You're not seeing any reflection off of its surface from the sun. A solar eclipse occurs when the Earth doesn't have light in an area because the moon is in the way. So the moon blocks the sun, causing a dark spot or an umbra to hit Earth through an eclipse. So you can actually see here that kind of idea of you have the moon in the way, and then the part of the Earth is completely dark as a result in a solar eclipse. So solar eclipses are the really spectacular ones to see. Lunar eclipses, not as spectacular at all, but solar eclipse is very cool to see. And if you watched that one 2 or 3 years ago, it's kind of neat. Other bodies in the solar system. Asteroids are small, rocky, or metallic bodies that are found in a belt between Mars and Jupiter, the asteroid belt. They can vary in size. They can be very, very large or tiny. And by large, I mean, hundreds of kilometers wide. I actually don't know the exact details, but I know they can be really big. Comets, also known as dirty snowballs because they are made of dust and ice as they travel through space. They do have a predictable orbit, but it does not follow the same model as the planet's orbit. So the difference between asteroids and comets is, number one, comets have a different orbit, and number two, comets are made basically of ice and dust, and they leave a tail as they move, which is residual dust and ice coming off of it, and eventually there will be none of it left as it just kind of gets eaten away as it moves. And of course, you know about Halley's Comet being the most kind of famous one. All right, that's it for part 1 of this lesson. I'm going to stop there, and then later on we will go through part 2.